we have three random variables, uniform. They are i.i.d. We're letting L be the minimum of these three and M the maximum of them. We're asked in part A to find the marginal CDF and the marginal PDF of M, and then the joint CDF and joint PDF of L and M. We're also given a hint here to consider this probability here. We're going to figure out why that hint is helpful. And then we're going to find the conditional PDF of M given L. Okay, so let's start by figuring out the CDF of M. So f of M, the CDF of this random variable, by definition is the probability of M being less than little m, and M is the maximum, I'm just using the definition of M, of these three random variables. And now we would like to open up this maximum and looking at what these what this random variable, the max, means is that all of these indeed has to be less than m, because if even one of them is larger, then this event will not be true. So if m is, for example, 2, and this random variable, well, u cannot be larger than 2, but let's say that it could for any random variable, then this u, if it was 3, for example, so larger than m, then this event cannot happen. So we'll be having probability 0. So all of these have to be less than m. So this is, the max is the same as u1 being less than m, u2 being less than m, and u3 being less than m. And this is very helpful because now we write it like I just did, and we use the fact that they are independent, which means that we can write them as ui being less than m. And now we have 3 of these, so if I write instead of 1, I'll just write I, so all of them times 3. And that is indeed going on here, and this is the same thing as writing, because of the PDF, the CDF of M, this is the same as writing M 3 times, because that's the probability. We have a uniform probability over that region. So that's good, and I should also point out that the support here for M goes from 0 to 1. All right, and the PDF is pretty straightforward, because we then just take the derivative of the CDF with respect to M, f of M, and that is what we just calculated, M3, which is the same thing as 2M, oh sorry, that's 3, M2. That's the PDF. All right, so that was sort of a warm-up to the other part of the question, which is to figure out what the joint CDF and joint PDF are. Okay, let's start with the joint. So this will be a function of little m and L, like so. And this is by definition the probability of L being less than little l, m being less than little m. over the support that they are defined for. Now, this in turn is the probability of the minimum of all the random variables, u1, u2, u3 being less than L. And here we have the maximum of u1, u2, u3 being less than M. So at this point, we can try to figure out what the at this point we can basically open up the same argument as we did up here, but the problem is that this part we can't really do, and figuring out the how to sort of, well, basically proceeding according to this path would lead us to a rather complicated calculation. So another part, and this is where the hint comes in, is to figure out what the using the law of total probability over the CDF of M. And let me just do this. I'll just write first ... here, and then proceed by figuring out what this is the CDF of M, which is what we just calculated. This is using the law of total probability here. Now, law of total probability is the same as M being, capital M being less than M for when L is less than little l, plus M less than M where L being larger than L. Okay, so is this any easier? Well, it turns out that it will lead us to an easier calculation, because what will happen here is that what we want to calculate is just right here. So by subtracting off this term from that term, which is what we calculated, we end up indeed having an easier calculation, because having L being larger than little l will allow us to open up this part in the same way as we open up the maximum. So the minimum will be easy to open up. Now let me show you what I mean by easy. So what is happening now is that we're going to take the probability. I'll do the following. Just move this equality, and we'll misalign it, but you'll see why in a moment. So I'll have probability of M less than M minus, now we're going to take this part, duplicate it, right, and we're going to take that part, duplicate it like so. Alright, so now we have what we want to calculate just sitting to the right. That's great, this is what we want. So instead of going through this calculation, we can go through that calculation, which is indeed a much easier one. We know what the probability of capital M being less than M, that is just M3. So I'm going to write it in here, minus, like so, and this we're going to focus now on the on this part of the argument. All right, so what is that part? Well, that part is, I'm going to continue this just right here, and this part is then the probability of max. Well, let me just copy this whole thing, and I'm going to write it like so. Remove this part, and then what we have is that we have the L being larger. That's the only difference. This is what we gain by this maneuver. But now, all of these, when they're larger than little l, that means that all of them have to be larger than L. So this is the same event. It's the same event as U1 being larger than L, U2 being larger than L, U3 being larger than L. And on the other hand here we have that being true for all events, so U1 being less than M now, U2 being less than M, and U3 being less than M. So this looks still quite complicated, but by starting to match the terms, basically what I mean by that is that we have the probability of Ui, so for all of this symmetry basically, U1 is larger than L but less than M, and the same for U2, and the same for U3. So what we have is Ui is larger than L, at the same time Ui has to be less than M, and we have that 3 times. Okay, and this is then the same thing as Ui must be less than L and larger than M 3 times. And this is because it's uniform. What we're saying here is that we have a region of where, if we look at the region of the CDF, is that we have, if M, well, basically what we're saying is that M is sitting here and L is sitting there, then we're also saying that the probability of falling into this region, because it's uniform, it's the same as M minus L to be in this region here. And so we can then proceed by writing M minus L immediately, like so. So basically, moving up to continue our calculation there, I'm going to just copy this, move it up here, and this is basically the CDF that we that was asked for to calculate the joint PDF. That's great. So now calculating the PDF, we have to take the derivative of that. Let me just copy of that CDF like that. So the joint PDF LM is the same as taking the derivative once with respect to M and then respect to L of f of LM, like that. And that is what we just calculated. So I'm going to move in this part here, I'm going to move in that part a little bit, so, and this we don't need anymore. Okay, so let's take the derivative with respect to m first, and then with respect to L. And so this is then just 3m2 minus m minus L 2 3, like so. And then we take the derivative with respect to L, so that's what we have left here. So now this term here disappears, it becomes 0, and this right term minus L, we have to take the derivative with respect to this inner term, so this becomes minus, so minus minus gives us plus. And this is indeed the PDF of the joint PDF of L and M. Okay, so let's now proceed to the other last part of this exercise, and that is to find the conditional PDF of M given L. All right, the conditional ML, like that, is L, oops, and just notice I'm writing these in capital letters, and these are in small letters to be consistent. One chooses one of these, and often we use the capital version of it. So just a note about that. And then here we take the joint, which is what we calculated just here. So the joint is just this part, put it in here. What we don't have is the PDF of L, and that we can calculate like by finding the CDF, which is at least in my mind easier to work with, and then take the derivative of that term. So this part here is the same thing as the probability of L being less than L, and that's the probability of the minimum. And basically that's what we calculated partially in the CDF, the joint CDF. Like so. And again, to open up that minimum, we take the complement so that we can change the direction of the inequality here, like that. And that enables us to calculate, basically use, we can now set this to be U1 larger than L, U2 larger than L, and U3 larger than L. And using the fact that they're independent, we can write any of these i's, I1 to 3, 3 times, and that is the same thing as 1 minus this thing here is 1 minus L. So we're going in the other direction, right? So it has to be the complement 3 times. But because we want the PDF, not the CDF, we take the derivative of this term. So the PDF here is the derivative of this. So f of L, it's going a little fast now. I'm making some mistakes here. F of L, and that is the same thing as 3, 1 minus L, 2. All right. So let's move this up then to the denominator, and we end up having 2 m minus L divided by 1 minus L squared. And there we go. That's the conditional PDF of m given L.